other machine learning models, and then we were going to talk about deep learning. So yesterday we talked about the linear regression model and the logistic regression model, and then the decision tree. And today we start to talk about the SVM, the support vector machine. So the support vector machine is a binary classification model. Yeah, it's just for the binary classification task. But if you want to do the, for example, 3 classification task, it's fine, but it just classify 1 class and others, and then in the others it will be binary classification task. So it can do the multi-classification task, but yeah, it just one by one to classify. Okay, and yes, there's an example here. The blue plus means the data of the man, and here the red circle means the woman. And we hope to classify the woman and the man. So there are a lot of line we can, yeah, there are a lot of lines such as this line can also classify this 2 class, and of course this line. Yeah, so how to choose the best line? That is a problem. So in SVM, the SVM hope we can get the maximum margin. So this distance means the margin. This line means the age of the man data, and this line means the age of the woman data. So the SVM hope, we can get the maximum margin, and the black line, just the middle of the margin, is the model. So can you get it? And yeah, the SVM only care about this data, but rather than others. So this data called support vectors. So the support vector machine only care about the support vectors. That is why if the number of the data sets is not so big, maybe it's more, but the SVM can also perform well, because it only care about the support vectors. But in this example, the SVM is only a linear classification model, right? Please mute.
Okay.
And then if some test like this one, we cannot use one line to classify these 2 class. So what can we do? There's another trick called the kernel tricks, or we can call it the kernel function. And we can use the kernel function, change this kind of data, put this kind of data to a hyperplane, and then we can use one linear classify to do the classification task. That is a support vector machine. So that is a kernel function plus the max margin. And that is a support vector machine. Okay, and then I will talk about another one. another model. It's called naive Bayes. So do you still remember the Bayes formula? That is a Bayes formula we talked about in the first day, in the Monday. So we can change the probability of given x, y into this item, the probability of the given y, x, and multiply the probability of the y and divide by probability of the x. So that is a Bayes formula. And in naive Bayes model, we need to use this formula. So I will give you an example. There's an example here. The task is to recognize the spam. So do you know what is spam? The trash email.
Yes.
Okay. So the task is to recognize spam and the normal email. So the X here is the email. And the Y means the output of the machine learning model. So is spam or normal. Oh, sorry. Spam or normal. So we can use the probability of given x spam divide by given x normal. So if the result is bigger than 1, that means maybe the email is spam, right? Can you understand? That means we have the given x means that we have a data set, one email. So that is a probability of this email is a spam, and here is the probability of this email, the normal email. Okay. So according to the Bayes formula, we can change the probability of given x spam into just like p spam given spam is email and multiply p spam and divide by px. And we need to divide by p given x normal, so it's just like p given normal x multiply the p normal. So here we can ignore the probability of the x. Can you understand?
Yes.
Okay, so we only need to calculate this part. Okay, and in naive Bayes, there's a hypothesis that is all the features are independent. So in the email, maybe it include a lot of words, and the words are the features. So that means the word win is independent with the play and the discount. So we can calculate this item by multiply or the words or the probability of the words, just like this. And then how to calculate the probability of given spam win. That means we can use the number of the spam, and the spam have the words win, the number of, and divide by the number of order spam. And then we can get this probability. So, can you understand? For example, there are 10 spam in the data sets, and 5 spam includes the win, the word win. So the probability of given spam win, we can use the 5 divide by 10. So that is 0.5. Can you understand?
Yes.
Yeah, that is same to calculate the probability of given span play, given span discount. So now we need to know how to calculate the probability of the span. We can use the number of the span, and divide by the number of all the email. So can you understand it? The probability of the span. Okay, thank you. So now we know how to calculate this item. So it's same to calculate this one. And then we can get the result. And if the result is bigger than 1, it means the email is more like a spin. So can you understand? Okay. But the naive Bayes not performs very well if the features are dependent. That means maybe some features like the height and the weight of a human. So we know if the number of the height is bigger, maybe the number of the weight is also bigger, right? So there are some relationships. Okay, thank you. So there are some relationships, they are not independent, and then the naive Bayes cannot perform as very well. Okay. And I will talk about the next model called k-nearest neighbors. That is very, yeah, please.
Understand the different types of naive Bayes.
Yes, exactly. So that is one of naive Bayes. I think it's easy to understand. Okay. So I cannot talk about all of them. So I only talk about one of them. Okay. Yeah, and next one I want to introduce that is k-nearest neighbors. So it's very easy to understand. There's a new data that is a white one, the white circle, yeah, and we need to find the k-nearest neighbors of new data. And the k we need to set the k value. For example, today we set the k is 4, and we get the 4 nearest neighbors. They are the yellow one, green one, and the red one. So can you tell me what is the color of the new data? Do you think what is the color of the new data?
Yellow.
Yes, exactly. It will be yellow one. Okay, and if today there's 2 yellow and 2 red, we can just set the weights for each neighbor. So for example, the weight of the nearest one is 4, and the second one is 3, third one is 2, and last one is 1. So we can just multiply the weights and hear about yeah, and do the final decision. So that is the k nearest neighbors. That's very easy to understand. Okay, and we will do a short summary of the traditional machine learning model, the linear regression model. Of course, it can do the regression task, but it is easy to underfitting. Because the linear regression model is very easy. Just to use one line or like this to distinguish to not distinguish. It's to predict the data. And the logistic regression is only use the sigmoid function and then change the L2 laws to the cross entropy laws. and then it's over. And it's also easy to underfitting. It's a linear classification model, and that means it cannot solve the XOR problem. And the next is a decision tree. The decision tree is easy to interpret, easy to explain, and it's powerful for unbalanced data. That means if there are two classes and one have 80% data and other had only 20% data, and that means it's unbalanced. But of course, the decision tree just do the decision. So for example, larger than 30 is 4 or equal than 30. So it can solve the unbalanced data. And if we want, the decision tree can fit all the training data because we can build a lot of leaf nodes. But if it's easy to overfit, and we can use the random forest to solve the overfitting problem. And the next one is the naive Bayes, the one of the naive Bayes model. Okay, and the model is for the classification task, and the performance of the model depends on if the features are independent. So if the features are independent, and the naive Bayes can work well, but the features are not independent, they are dependent, and the naive Bayes cannot work very well. And the next one is the k-nearest neighbor model, and it also can do the classification task. And the problem is the key value will influence the performance. So we need to set the key value, and of course the weights I mentioned before. So it is a little bit difficult to set. So we need to have the experience of the task. Okay, and the last one is a support vector machine, and it's the binary classification task. It's work for the binary classification task. And actually, before the deep learning, the SVM is one of the best model. It can even perform very well if the number of the training data is small. So that is a traditional machine learning model. And do you have any questions? Okay, so there's a quiz.
Do you mind repeating about the SVM and the kernel? If you can go back to the previous slides where you were saying yeah, here, thanks. Do you mind just repeating this?
Okay, so the SVM hope we can find the maximum margin, and this point called support vector. So the SVM only care about the support vectors, only this data. That is why if the number of the data is not so big, but the SVM can also perform as well. And this model is only a linear classification model, but we hope to solve the unlinear data set. So we need the kernel function to put this kind of data into a hyperplane, just like this. It's a three-dimensional plane. And then we can classify them just like this. And there are a lot of kernel function. For example, the Gaussian kernel function, and you need to choose one of them. And it depends on the tasks. Okay, clearly?
Thank you, yeah.
Okay, you're welcome. Okay, and there's a quiz here. The logistic regression model is used to deal with the regression problem, yes or no? True or false? Hello, my friends. True or false?
Is it false?
Yes,
It's true.
it's false. The name of the logistic regression treat so it's
It's used for classification, is it not?
yeah, exactly. It's used for classification task. Okay, you need to remember it. Okay, thank you. And then I will tell you something about the hyperparameter. So the hyperparameter is the parameter that we cannot change it and during the training. So for example, yesterday, one friend talked about the learning rate, right? The initialized value of the learning rate, how to choose a suitable value for the learning rate. The initialized value we need of the learning rate we need to set, so it cannot change during the training. I mean the initialized value. So of course the k value in KNN it cannot change, and of course the initial value of the weights and the bias in linear regression we also cannot change during the training. That means these parameters are hyperparameters. That means we need to set by ourselves. So actually the job of the AI engineer is to choose a group of the hyperparameters. Okay, and actually there are lots of hyperparameters in deep learning, the neural networks. So yesterday, someone asked me how to search the hyperparameters. Yeah, there are some methods. For example, the grid search, random search. The grid search means search the parameter one by one. For example, there are two parameters. The row means one parameter and hyperparameter, and the column means another hyperparameter. We need to search one by one by one. That is a grid search. Okay, if there are only two hyperparameter we need to search, we can use the grid search. One or two hyperparameters, I mean. If there are more than three, we cannot use the grid search because it needs a lot of compute power. And then we can use the random search. It's quickly, but maybe we cannot find a best group of the hyperparameters. And if in the deep learning, the neural networks, okay, there are lots of hyperparameters, and we can use the meta learning to train another neural networks to find the group of the hyperparameters. Yeah. Okay. And how can we know the performance of the group of the hyperparameters? We can use the k-fold cross-validation. We know we can divide the whole data set into the training set and the test set, right? We talked about yesterday. But the k-fold cross-validation means we can divide the training set into k parts. For example, 1, 2, 3, 4 here. We divide the training set into 4 parts. And in the first training, we only use this part, and this part as the training set. So we will use this data sets to train the model. And then we need another set called validation set. So the validation set will not, we will not put the validation set into the model when we train the model. So it's just like the test set, we need to use it to test the performance of the model. And that is the first training. Yeah, at the first. And in the second one, we need to use this part of the training set as a validation set. And this part we need to put back to the training set. So that is a second training. And the third training, we need to use this part. And the fourth training, we need to use this part. That is a k-fold cross-validation. So why we need to use the k-fold cross-validation? If we have only a small number of the data sets, maybe one-time training, we cannot get the a very good result. So that means the result may be higher, maybe lower. So we hope the result is not random. So we can just train k times, and then we will know the performance of the machine learning model. And can you understand?
Yes.
Okay, so the k-fold cross validation is only used for the small number of the data sets. And if we have a lot of data sets, maybe we train one model, we need to use several ways. So it's not suitable for a large number of the data sets. Okay. And yeah, there's a quiz. The hyperparameter cannot be changed in model training. Yes or no?
Yes.
Yes, exactly. Yes. Okay, so that's the content for machine learning. And then we were going to talk about the deep learning. We need to speed up because I have a lot of things I want to share you. Okay, so what is the difference between deep learning and the traditional machine learning model? I mean, yeah, of course, deep learning is a subset of the machine learning, but we need to compare the traditional machine learning model and the deep learning model. So the deep learning model needs more data sets and more compute power. And the deep learning model can solve more complex problem, just like the face recognition or just the Go play. And sorry, mute it, please. And the deep learning model is a neural network, we know, and we can think the neural network as a black box. That means we don't know how it works, but we only care about the input, that is the data, and the output. The output depends on the tasks. Okay, so it's end-to-end training. We only need to care about the input and the output. And in the machine learning task, we need to select the data sets and clean the data sets. But in deep learning, we only need to care about the data and the output. Okay, but the disadvantage of the neural network is it's hard to explain. It's very hard to explain. So we don't know why the AlphaGo choose this step. And the AlphaGo will never tell us why this step choose this position. So it's hard to explain. Okay, can you understand it? Yeah, do you know the difference? Okay, so let's continue. And now, finally, we will talk about the neural networks. Before talking about neural networks, we need to talk about the perceptron. And the perceptron is just like this. The X here means the features of the data sets, and the W here means the weights, the parameters of the model. When we train the model, we need to update the parameters. Okay. And yeah, that is a perceptron, and it cannot solve the XOR problem. You need to remember that it cannot solve the XOR problem because it only had the input layer and the output layer. There's no hidden layers. Okay. So we have the neural networks. The neural networks means we can have a lot of the hidden layers. Here, the input layer means the features of the data. For example, the height of the human and the weight of the human and the age of the human. So each neural in the input layer means one feature in data sets. For example, okay, that is the height, weight, and that is age. And here, the line between one neural to another neural, that is a weight. Of course, it's also a number. So each line means one number. And that is the simplest neural network. It's called fully connected neural network. That means this layer, each neural will connect with the previous layer or the neurals in the previous layer. For example, this line, and this line. Connect with all the neurals in the previous layer. Can you understand?
Yes.
Okay, thank you. So each neural is a number. And how to calculate the value of the X? We can just use A1 multiply, that is A1 multiply the W1, and add the A2 multiply the W2, and plus the A3 multiply the W3, and plus there's a bias of each neural. So we also need to add a bias. Here, the bias, of course, that is another value. Okay, so can you understand it?
Yes, okay.
Okay, it's all for the neural network. It's a joke. Okay, so it's the first step we understand the neural network. And that is the output layer. That means, yeah, the number of the neural in the output layer depends on the tasks. For example, if we do the binary classification test, we can use 2 neurals. This one means the probability of the first class. And this neural means the probability of the second class. So we only care about the input layer, that is the features in the data set, and then we only care about the output layer. The output layer depends on the tasks. Okay, and then the hidden layer, just like the blackboards. We don't know how it works, but it can work very well. So that is a neural network. It's very important. You need to know how to calculate each neural. And yeah, there's a quiz. The perceptron can solve the XOR problem, yes or no?
False.
False.
Sorry, I didn't understand the previous page. There's a question. Can you go back?
Yes. Which question?
Okay, not here. The last page. Next. Next.
This one?
The immediate page, the neural network.
The neural network. Here.
Yes, this one.
Okay, so
When you say we we don't know what is happening in the neural network. It's a black box. What does that mean?
It means we don't need to care about the hidden layer, the values in hidden layer. Of course, it will calculate all the values in the hidden layer, but we don't need to care about them. It has maybe no meaning, but the input layer and the output layer has meaning.
Okay.
Okay, so do you have any
Can you give me
other?
an example of the output layer? I mean, the output of a neural network. I heard someone talk of binary classification, but I
Yes.
don't know how that flows through the layers so that the output is either 1 or 0.
Okay, yeah, there's another example. If we have 3 class and we will do the 3 classification task, and
Yeah.
each value in the output, each value in the neural of the output layer, that means it will be the probability of this class.
Okay.
So when we train the neural network, we need to use the probability to calculate the loss value. So we talked about yesterday, the loss
Yes.
value. We need to define a loss function. And when we do the prediction, we just need to choose the maximum probability. For example, that is 0.8, 0.1, 0.1. We will choose, the neural network will think, okay, maybe it belongs to the first class.
First choice. Okay.
Yeah, and then it will output 1, 0, 0, like this. It means the first class. But it's
Okay.
only in the prediction. We need to calculate the 0.8 when we train the model. Okay.
Okay.
Yeah, thank you. And then we will talk about the activation function. It's a very, very important part in the neural network. So what is the activation function? We can use one vector to indicate the input layer. I use the same color, just like this. Can you understand? That is a vector, 3-dimensional vector. And then this layer, the weight in this layer, we can use one matrix to represent. For example, there are 12 weights, right? 3 by 4. The number of this layer is 3 and this layer is 4, so there are 12 weights. Do you agree?
Yes.
Okay, so the number of the matrix here, the number of the rows is 3, and the number of the columns is 4. So we can use this matrix to represent the weights in this layer. And that is the same in this layer. We can use another matrix. I use another color. It's 4 by 4 matrix. Here is 4 by 2 matrix. Do you agree?
Yes.
Okay, so when we multiply the matrix, we can just multiply this 3 matrix and then multiply the vector. So it's same. Okay, and that means the matrix multiply another matrix, we will get a new matrix. And we will use the new matrix to multiply the blue matrix, and then we will get a new matrix, the red matrix. It means if we build if we have 2 hidden layer, it's just like we have no hidden layer, right? There's only one layer. So that is a problem. It's no meaning we build a lot of hidden layers. So how to solve this problem? We need to use activation functions. Just we need to, when we calculate the value of the x1, the value of this new row, and we need to put the value into one activation function, just like the sigmoid activation function. Yeah, the sigmoid is this one. And yeah, we put the x1 into the sigmoid function, and then we will get a new value. And then we will put the new value into this new row. And that is the final value of this new row. Okay, can you understand? So let's talk about some activation functions. Okay, the first one is the sigmoid. We use sigmoid in logistic regression model, and the sigmoid can also used as the activation function in neural network. The sigmoid is just like this. The red line means, yeah, the sigmoid function. And the blue line means the derivative of the sigmoid function. So why we need to talk about the derivative, I will tell you later. So the input of the sigmoid is the x here, and the output is the y here. So if we input the 8 here, the output will close to 1, right? So now we get the x1 equal to a1 multiply w1 add blah 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 a3 multiply w3 plus bias, and then we get the number the value of the x1 is maybe 8, and then we will input the 8 into the sigmoid function, for example, and then we will get the output is close to 1, maybe 0.99, and then the 0.99 will be the final value of the x1. Okay. Can you understand?
Yes, okay.
Okay, thank you. So that is the first activation function. And the next one I want to introduce is a 10H function. Just like this, the output, the range of the output between -1 to 1. And the derivative is the red line. So what's the problem of the sigmoid function and the 10H activation function? Here, the range smaller than -4 and bigger than 4. The derivative of the sigmoid function and the 10H activation function are very, very small, close to 0. Do you agree? That means if the input of the 10H activation function is equal to 100 and another input is equal to 8, yeah, of course the 100 is much bigger than the 8, but the output will similar, close to 1. Do you agree?
Just repeat that last bit.
Sorry, you can understand?
No, I can't understand.
Okay, so that is a sigmoid function. I will clean them. The x means the input of the 10H, and the y means the output of the 10H.
Okay.
So yeah, if we input 8, the 8 is here, the output will be
1.
close to 1. Okay. And then if we input 100, and the output will also close to 1,
Yes.
right? So that means the derivative of the 10H in this range are close to 0. And it will cause the vanishing gradient problem in neural networks. That means, okay, the 100 is no meaning. We only need the 8. The 8 is equal to the 100. Okay.
Up to infinity, yes.
Okay, that is a problem. So
Okay,
you're welcome. So how to solve the problem? You can use another activation function. It's called ReLU activation function, the ReLU. And the ReLU is very, very easy to understand. If the input is smaller than 0, just like this, and the output will always be 0. And the input is bigger than 0, and the output will equal to the input. Just like this. So the derivative of the range here will always be 1. Do you agree?
yes.
Yes. So it can solve the vanishing gradient problem. And then I will give you a experiment. So please.
Hey, Kiki.
Oh, what's wrong?
No, that's how you.
Can you? Okay. Well. Excuse me. Who is the user 46? Can I use your notebook? Because I cannot start my notebook.
How much are you going to pay me? You can use it.
Sorry. Oh, what's wrong?
Okay. I've stopped it.
No. You don't need to stop it.
Oh, okay.
Sorry, I will change the internet. Okay, it's fine. Yeah. So can you see the sigmoid with ReLU here? So open the Jupyter file, sigmoid with ReLU. Yeah. Can you see that? This file?
Yes.
Okay, I will change another kernel. Okay, so let's run it. Okay, before run it, we can change here. It's fine if we use the 10H here. So I will explain the experiment. This experiment, we do a image classification task or image recognition task. And we use the MList as a dataset. So there are 10 classes in the dataset, the number 0 to number 9. Okay, just wait a minute. And in this experiment, we use the Keras. Do you still remember the Keras framework? I talked about it. It's easy to use, but it uses the TensorFlow backend. So we need to install the TensorFlow, and then we can use the Keras. Okay, so this task is a image recognition or image classification task. We have 10 class. They are number 0 to number 9. And they are images. And then the shape of the image is 28 by 28. So each image, the shape of each image is 28 by 28. And we just build a neural network here, 28 by 28. And we build a network that has 30 layers, hidden layers, 30 hidden layers. Okay, and in each hidden layer, we have 100 neurons. So that is a very simple neural network. And here, we need to choose the activation function. So the activation function is one of the hyperparameter. Do you agree? We need to set it.
Yes.
Okay, thank you. So, and then we can just, train this neural network. After 5 epochs, we find that the accuracy is equal to 11%. That means we cannot train this neural network, right? The accuracy is too low. It's just similar with guess a class randomly, right?
Yes.
So we cannot use the sigmoid activation function to train this neural network because it's too deep. If the neural network is too deep, it will cause the vanishing gradient problem. That means the previous layers, we cannot change the weights because there's no gradient. And then we can change the sigmoid to ReLU. Just change the sigmoid to ReLU. Finish. And then we run it again. Okay, let's see the structure of the neural network. It has 32 layers, 1 input layer and 1 output layer, and 30 hidden layers. Okay, look at the accuracy. Now we get 70% accuracy. So that means we can train this neural network. Although the performance not so well, but we can train it. Do you agree?
Yes.
So the ReLU activation function can reduce the vanishing gradient problem. Okay.
About the softmax in there.
Okay, I will tell you what is the softmax. Just in here, the softmax activation function, we can change the score of the neuron into the probability of the neuron. For example, the score can be 100, but the probability will, sorry, that is not the sigmoid. The probability, the range of the probability will be between 0 and 1, right? And here, there are 10 class. So the 10 probability, if we add all the probability, it will be 100%, right? Do you agree? So we add all the probability of all the class, it will be 100%. So it's just like the softmax can change the score to the probability. So we always use a softmax activation function in the output layer when we do the classification task. Do you agree?
Yeah, it now makes sense. I was almost asking the same question of softmax even before Edward asked.
Okay. And so there's a question, why we need the softmax? Why we need the softmax? When we do the prediction, we only need to choose the maximum value, right? We don't need to change it to the probability. We only need to choose the maximum value as the final result, right? For example, the first class has the maximum value, and we only need to choose this class as the final result. But when we train the model, do you remember the label of the classification test? It will be one hot. That means only one dimension has the value of the 1 and others will be 0. And we need to calculate the distance between the prediction value and the label. Can you understand? So if the probability here is 1 and others are 0, that means there's no distance between the prediction and the label. So the loss value will be 0, right?
Yes.
Okay, but if the value is 100, we cannot calculate the distance. For example, this is the 100 and others are 0. We cannot calculate the distance. Do you agree?
Yes.
So we need the softmax. Okay, makes sense.
So does that also bring in the point of just to make sure that the model is not overfitting, basically to just make it more generalizable?
Yes, it may be overfitting, but that is only an example. So help you understand the softmax. Okay. If the loss value is very small in training data, it may be cause the overfitting. But the loss value in test data is small. That means the model performs very well. Okay. So this data maybe not the training data, but the test data. Okay. Can you understand?
Sorry to take you back. I missed the difference between the test data and the training
data.
Yes.
Okay, I will explain. So we have the data sets. For example, in the data sets, there are the images, right?
Yes.
Okay, so we will divide all data sets into the training set and the testing set.
Okay.
So we only use part of the data set to train the model and use the test set to evaluate the model.
Okay. And the validation, what's the difference between test data set and validation?
Okay, the validation, we will, here we just use the training set. And we will divide the training set into K folder. And one of this part will be the validation set. The validation set is just similar with the test set, but
For the training.
yeah, it will not put this validation set into the model when we train the model. It's just like the test set, but the validation set used to evaluate the hyperparameters. It only used in the K-folder cross-validation. If you don't need to use the K-folder cross-validation, you don't need to set the validation set. You only need the testing set and the training set. Okay?
Okay, thank you.
Yeah, you're welcome. So let's take a break for 10 minutes. Do you agree?
Yes.
Yeah, thank you so much. Hello, do you come back?
Yes.
Okay, welcome back. So there's a quiz. Compare with the sigmoid function, ReLU function can reduce the vanishing gradient problem. So do you agree?
That's true.
Yes.
Of course, it's true. Thank you so much. It's true. Okay. So then we will talk about the training rows. And do you know how to train the model? Actually, we can use a gradient descent. That is a G, okay. Okay, so what is a gradient descent? Actually, very easy to understand. We only need to calculate the derivative of the loss value to one weight, and we can use partial loss to partial weight to calculate the gradient. Do you agree? The derivative. If you can understand it, that's fine. You just need to remember. That means we need to find the lowest point in this graph. For example, there's two weights, the weight 1 and the weight 0. And now we're here. And we want to find the lowest point. Here the E means the lowest value. Okay. So we only need to go to this point step by step. So we calculate one derivative and then calculate update the weights one time, and then calculate the derivative again in this point, and then update the weights again. So you only need to remember we can use the gradient descent to update the weights. We can use the gradient descent to train the models. Okay. We can also use the gradient descent to train the linear regression model or the logistic regression model or the SVM. It's fine. Okay. And there are some. Yes, please. I know you had a question.
This gradient.
So
how,
you can.
How long is the gradient? When you say you calculate one step and then the next step and then the next step, how long is the step?
Good question. We only calculate the gradient here, but do you remember we need to set the learning rate?
The what?
Learning rate.
Oh, yeah.
So we need to learning rate yeah, we need to multiply the learning rate and the minus gradient here. Okay, and then update the weight.
Ah, okay.
Okay, yeah. That is a new weight.
Okay, I've understood.
So that is the learning rate. Okay, very good question. Okay, so there are some.
Sorry, there's
Great.
another question.
Yes.
I'm not sure whether this is the right point to ask about the soft margin cost.
Soft margin. Okay, so that is in SVM, right?
Yes.
The time is limited. We can talk about after class. It's fine.
Okay.
Okay. Yeah. Thank you. Okay. So yeah, that is how we update the weights. Okay.
Okay.
Yeah. Then we use the gradient descent, and then there are lots of algorithms of the gradient descent, and the first one called the global gradient descent algorithm. That means when we train the model one times, we use all the data sets, or the training data set. I mean, the training data, we use all the training data. So we use all the training dates, calculate the gradients of all the training dates, and then we update the weights one time. There's a problem, just like there's an example. I lose the weight in supermarket and I hope to get the, I hope run out, but I lose the weight. So the global gradient descent means I ask all the staff in the supermarket, and then I choose a direction. But there's the problem is it's very slow to ask all the staffs. Do you agree?
Yes.
Okay, so that is a global gradient descent. The steps here is the data sets, the training data sets. Okay, and another one called SGD, that is a stochastic gradient descent. That means when we train the model, when we update the weights, we only use one data to update the weights. Okay. Only use one data. Just like I only ask one person in the supermarket. But the problem is maybe the person don't know the direction. So maybe it will tell me a wrong direction. Okay, so that is a disadvantage of the SGD, but the advantage is it updates very quick. Do you agree?
Yes.
Okay, so there's the last one called the mini batch gradient descent. We can use part of the training data, part date in the training data, and calculate the weights and update the weights. Okay. Calculate the gradients and update the weights. Only use part of the data. And then we need to set the number of the data. For example, the batch size, that the number called the batch size. And we can set, for example, 32, 40, 84, for example, here. So we only use part of the data to do the gradient descent. Okay, so we always use the mini batch gradient descent when we train the neural network. For example, in the last experiment, the default batch size is 32. So we input 32 images and train the network. Okay. And then we have a short summary The BGD means we use all the data sets, so it's stable, but very slow. And it's easy to throw into the local minima. The local minima means like this. If we go down from this point, it will stop at this point. Do you agree? And the SGD, the batch size is 1. That means we use only one data to update the neural network. And the advantage is it's quick, but the disadvantage is maybe we will get the wrong way. Okay, and the mini batch gradient descent, we always use this one. And it updates quickly and quite stable, and it can jump from the local minima. You only need to know that. Okay, and there's a quiz. Gradient descent algorithm can always get the global optimal solution. Yes or no?
False, B.
No.
No. Exactly. Okay. So if you train the same model a lot of times, you will find maybe the performance are different. Okay. That means maybe it will stop at the local minima. Okay. That is a global minima maybe. Okay. And then you maybe hear about the backpropagation. So what is a backpropagation? What is the relationship between backpropagation and gradient descent? Actually, we know we need to calculate the derivative of the loss value and one weight. We know when we do the prediction, the calculating direction is from the input layer to the output layer. But when we train the neural network, we need to calculate the loss value first. So that means we will get the loss value of the output layer. And then if we hope to calculate the derivative of this weight, we need to calculate the derivative of this neural first, and then we can calculate the derivative of this value. It's called train rule. So do you know that? Okay, thank you. So the value of this neural depends on this weight. So we need to calculate the derivative of these layers, and then we can calculate the derivative of these layers, and then we can calculate the derivative of the weights in these layers. That's called the backpropagation. So the direction is from the output layer to the input layer. Okay, so there's an example. If you are interested about it, you can just calculate. Okay, and there's a quiz here. We usually use gradient descent-based algorithm to train neural network models. True or false?
I think it's true.
Yes, that is true. Okay, so there are still some other methods, but usually we use a gradient descent because it's quick and the performance is well. Okay, and then I will talk about another two neural networks. One of them called the convolutional neural network, and another one called the recurrent neural network. So what is a convolutional neural network? It is a fully connected neural network. So do you still know how to calculate the value of the neurons?
Yes.
Here. Okay, so what's the problem of this neural network? If today the input layer is a very big image, for example, the image has, for example, 20 million pixels. And we need to use one neural to store 1 pixels. Okay, and that means we need to use 20 million neurals to store this image. Maybe we need more because it has 3 channels as RGB images, so we need to use 600 million neurals to store the image. And the weight will be very, very huge. The number of weight are very huge. Do you agree?
Yes.
So can we just reduce the number of the weight? Of course we can. We can use a convolutional neural network. So that is the convolutional neural networks. And there are 3 parts. The first part called the convolutional layer. And the second part called the pooling layer. And the third part called the fully connected network, the fully connected layer. So we also use, for example, this one in the convolutional neural network. So here we use the fully connected layers. Okay, that is the output layer. So that is a 3 class and the classification task. Okay. And now we will talk about what is a convolutional layer. That is a convolutional example of the convolutional layer. It's the input image as 5 by 5 image, and it is the convolutional kernel. And the number of the kernel are the weights. So we need to update the value here. For example, the 1, 0, all of them are the weights. So how to do the convolution? We only need to put the kernel in this position first, and then calculate by, we need to put it on this position, 1, 0, 1, 0, 1, 0, and 1, 0, 1. Okay, so we can do the convolution just like 1 multiply 1 in this position, and 1 multiply 0 in this position, and here plus 1 multiply 1 plus 0 multiply 0 plus 1 multiply 1 and plus 0 multiply 1, 1, 0, 0, 0, and 1, 1. So what is the result? 1 here, 1 here, 1 here, 1 here. It will be 4. Do you agree?
Yes.
So we put the value of 4 in this position. That is the output of this convolutional layer. The output is this matrix, and in this position we input the 4. The 4 calculated by this, and it called a convolutional. We do the convolutional and get the value. Okay, and then how to get value here? We only need to remove. Okay, I will remove all the painting here. Okay, so we just need to remove the kernel in this position and do the convolution again. And then we will get the value here. And move the kernel in this position and we get the value here. Okay, and then we just move the kernel in this position and get the value here. So can you understand it?
Yes.
Okay, so
But
that is
how do you get the filter values? 1, 0,
so
1.
yeah,
Where do they
the
come from?
values here are the weights.
Okay.
So we need to train the convolutional neural networks and update the weights here by gradient descent. Okay.
Okay.
Okay, thank you so much.
Which type of kernel do you use, and how do you select the type of kernel you use?
You mean the size of the kernel?
Understand is the linear or radial basis or polynomial?
Excuse me, I can't understand. You mean the size of the kernel? Or you're...
The kernel is one of the hyperparameters which we'll definitely use to set, but then there are different types of kernels. So basically just asking about the type of kernel, like now the one.
So the size of the kernel is a hyperparameter. You need to choose by yourself. You can choose 3, you can choose 5, but yeah, 3 is better. Okay, and
I think he's talking about the type, not size, type.
you mean the type of the value?
Type of kernel.
Type of kernel. The kernel just like the matrix. That is a matrix just like the image. Okay. And the value, the type of the value here should be float. Okay. So I can't stand what is the type of the kernel, but the kernel, we always use the matrix or a lot of matrix to represent one kernel. I will show you later. So, what's your question?
I think
Generally,
we can.
the kernels, there are different types of kernels, but it's okay, we can pick that up later.
Okay, yeah, thank you. Okay, so how to calculate the value? Just like this, move the kernels to order position, and then we can get one feature map, just like this. Okay, so that is convolutional operation, but if the image is RGB image, that means there are 3 channels of the images. And then how to do the convolution? We need to use one kernel, which kernel has also 3 channels, just like 3 matrix, and use this matrix to do the convolution in this channel of the image, and use this matrix to do the convolution in this matrix, and use this kernel, this channel to do the convolution in this matrix of the image. And then we will get 3 value, right? For example, 3, 4, 5. And we will add all of these 3 value. For example, it is 12. And then we add the bias. It will be 16. And we will put the 16 into here. Of course, that is just an example. You can calculate by yourself. And then there's another problem is there are a lot of 0 outside of the image equal the padding. So if we hope to control the size of the output, we can use the padding. Just like at one circle of the 0 outside of the images. Okay, and then we can also use a lot of kernels. Attention here. there's one kernel and there's another kernel. So we can use this, the first kernel, to get this matrix, and use this kernel get this matrix. That means the output image has two channels. Okay. So the number of the channel in one kernel, it depends on the input, the number of the channel of the input, and the number of the kernel will influence the number of the channel of the output. Okay. So can you understand? If you can, it's okay. We can see the experiment. Okay, and then there's another attribute called stride. That means when we move the kernel, we can move one step or two steps. If the stride is 2, we can move 2 steps, like this. Okay. Understand?
Yes.
Okay, thank you. So that is a convolutional layer. We will input one tensor. Of course, that is the image, and there can have a lot of channels in this image. And then we can use a lot of kernels to do the convolution, and then each kernel have one bias value. That is a scalar, is only a value, and we will add the value into the output. Okay, and then we will input the output into activation function, just like the ReLU, and then we will get the final output. That is the convolutional layer, just like this. Okay, and there's a second layer called the pooling layer. Yes, please.
On the bias, where do you get the bias values? Where do they come from?
Of course, the bias value is also the parameter.
Okay.
So we need to train the bias value by the gradient descent. Yes.
Okay, okay.
Yes. Okay. Good question. Okay, and there's another type of the layer called the pooling layer. So what is a pooling layer? The pooling layer is only use the window like 2x2 matrix here and choose the maximum value. Just like here, it's 56, and we input the 56 into the output matrix. That's called the max pooling. So the average pooling means we will calculate the average value, and then we input the average value into the output matrix. Okay, so there are two main pooling, the max pooling and the average pooling. So we will move the window from here to this position by 2 steps, okay, and then the maximum value here is 48, and the maximum value here is 255, and here is 32. So we can get a smaller feature map that is that called a feature map by the pooling layer. Do you agree? If the stride is 2, so we always use the stride bigger or equal than 2. Okay, so we can get the smaller feature map. That means we extract the features in the image. Okay. So can you understand it?
Yes.
Okay, thank you. So after a lot of, for example here, of a lot of convolutional layers and the pooling layers, we will get a lot of smaller feature maps. Because maybe we can use more and more kernels to get more feature maps. But the size will be smaller because yeah, we just do the downsampling, extract the features in the images. Okay, so and then we can put all of the feature maps into the fully connected layer and do the classification task. That is a convolutional neural network. Okay, so do you know the AlphaGo is also used the convolutional neural network, but there's no pooling layer because the pooling layer will lose some information of the images. The board of the Go play is 19 by 19 matrix, so we can also think that is a matrix, and also that is images. Okay. So the AlphaGo also use the convolutional neural networks. Okay, and then there's two main concepts of the convolutional neural network. The first one called local receptive fields. That means when we do the convolution, we only care about part of the images, but we will not care about all the images. Do you agree?
Yes.
Okay, and yeah, thank you. And the next concept is called parameter sharing. So that means we only need one or more convolutional kernels in one layer. Yeah, the number of parameter of 3 by 3 kernel is only 9. So we don't need a lot of weights in one layer in the neural network. So that is how to reduce the number of the weights. Okay. So we only need to small number of the weights in convolutional neural networks. Okay, there are 2 quiz. And after quiz, we can go into the experiment. Okay. So the first one, convolutional neural networks are commonly used to process images. Yes or no? Yes or no?
It's true, yeah.
Yeah, that is true. Yeah, exactly. That's true. Okay, the second one, when the input are the same, the feed-forward neural networks or the convolutional neural networks will always have the same outputs. Do you agree? That means if we train a neural network and the parameters of the kernels were fixed and the output will be same. Do you agree?
I don't agree.
You don't agree. So why? If the input are same.
I'm not sure.
It's true. For example, this example, if we get the convolutional kernel just like 101010101, and the output will be same if the input is same. Do you agree?
Sure.
Yeah, sure, of course. So why we need to ask this question? Okay, of course, after that, we need to learn about the recurrent neural network. But before that, we will do the experiment. So open your Huawei Cloud, please. And okay, fail to start. Oh. Sorry about occupy your notebook. I'm so sorry. So
Send me an invoice.
So can you see the file named CN train? Just open it. Okay. Before we run the program, we need to here new and choose the terminal. Can you see that? The terminal.
Yes.
And we need to just follow me. We need to open the terminal and use the command ls and show the files in this path. So there are a lot of folders.
Excuse me.
Can you follow me? Just new and terminal here.
Okay, okay, okay.
Yes. And then use the ls. We'll find a lot of folder in this path. And then we use command cd and work. Enter the work folder. And then use ls to show the files. Okay, that's our notebook path. Okay.
Yes.
And then we will use this command wget, and you need to input the address of the website. You can find the address in the lab guide. But if you don't want to open the lab guide, just input the address.
Sorry, could you go back slightly on accessing the console on it? My computer had hung.
So you cannot
No,
open
now I can enable. Yeah.
Okay. I'm so sorry. Maybe there's some bugs of the Oracle. Yeah,
I've accessed the train. Yes, I've accessed the train. Where do I go?
Here, right?
Yes, I'm there. Yes.
Yeah, so we need to download the datasets first. So just follow me, open here. Open the terminal. Here. And then cd work. And then wget and input the address. And then we have downloaded the datasets. Just check it. There's a dataset called flower photos, and we can unzip it. Okay, just use the unzip flower photos like this to unzip the file. So, do you finish?
No, I'm behind. I'm sorry. From after ls, what do I do?
Yeah, first you need to cd the work. Cd the work and use ls to check the files in the work. And then you need to use the wget and type the address to download the datasets. Okay. If you can follow.
Which address?
Yeah, this address. This address, you can take a photo.
Okay, just pause there. I take a photo.
Okay. And then
Luca, can you copy the address and paste it on the chat? In the chat, is it possible for you to do that?
You can copy the address
Okay,
in the lab guide. Yes.
Okay, that's right. Okay, right.
Yeah. And then unzip the file. Because the time is limited, if you cannot follow, just look at me. And then you can follow the lab guide. Okay, after class.
Okay.
Okay. And we get the file now, and then we can do the experiment. Okay, that is a CN model experiment. Just run it. Okay, the task is to classify 5 kinds of the flowers. And we have just like the daisy and sunflowers and the rose. We have 5 different kinds of the flowers. And we need to do the flower classification task, okay? And the input image, the size of the input image is 100 by 100. And there are 3 channels, the RGB channels. So red channel, the blue channel, and the green channel. Okay, and this cell is to read the images, okay? And then we can print the shape of the data sets. There are 3,670 images, and each image we have 100 by 100 matrix, and there are 3 channels, the RGB channels. Okay, and the label we have, of course, the same number of the labels, and we print the first 10 labels. They are 0, 0, 0, 0, 0 means the first class. Okay, the second class we will use 1, 1, 1, 1, 1. Okay. That is the first image, the label of the first image, that is 0, and we will change it to the 1 hot vector. Okay. And then we shuffle the data sets. Just shuffle it and split the data. We need 80% data as the training data and 20% data as the test data. Okay, so the number of the training data, we have about 3,000 flowers. And the test data, we have 700 flowers. And then, do you still remember the placeholder?
Yes.
Okay, yeah, thank you. And then we build a convolutional neural network in this cell. So that is the first layer. The input of the images is 100 by 100. And here we use the 5 by 5 kernels here, 5 by 5 kernels. And that is a channel of the kernels. So the channel should be same as the channels of the input. So the channels of the input here is 3. So we have to use the number of the 3 channels in the kernel, just like the 3 have to same as the 3 here. That is the images and that is the kernels. And then we use the 32 kernels. And here we add the bias, and here we do the convolution. So the stride we use 1 by 1. So this 4 number means the batch size. Maybe we need to do the convolution in the batch size, but we always set here is 1 in image. Okay, and here that is the rows and the columns. So we set the stride as 1. That means each move we just move 1 step. Okay, and the last one is the number of the channels. We always set 1 in image. Okay, So here we use the same padding. That means if the stride is 1, and we will not change the shape of the feature map. So we don't care about the size of the kernel. We will get the same shape of the feature map with the input. Okay, so that is 100 by 100, and the output will also 100 by 100. Okay, that is the same padding. That means we add a lot of 0 out of the images. But attention here, if the stride is 2, it will be different. You can check how to calculate the output size with the same padding. Use this formula. Okay, and there's a question here. What number of the channel of the output in the first convolutional layer? The number of the output channel. Yes, the size of the output channel will be 100 by 100. So if we use the same padding, and the size of the output images or output feature maps will be same as the input. So the size will be same, but the channel can be different. So how many channels in the output feature map? The number is same as the number of the kernels. So the channel will be 32. Okay. Each kernel we will get 1 feature map. So there are 32 kernels, so we can get 32 channels. Do you agree?
Yes.
Okay, so, and then we will build a pooling layer here. The size of the pooling layer is 2 by 2, and the stride is 2, 2. So we will get a smaller feature map from 100 to 50. Okay, just like the example in the pooling layer. Okay. So what's the number of the channels here? The output of the pooling layer?
It's still 32?
Yes, it's 32, exactly. Thank you so much. And then we build another convolutional layer here. Yeah, the third convolutional layer. And we use the kernel size 5 by 5, and the channel here is 32. Why? Why the number of the channel is 32?
Is it because that's the output from the first layer, or is it the second layer of the channels?
Yes, exactly. So the input of the layer is 50 by 50 feature maps, and the number of the channel is 32. So the number of the channel in this convolutional kernel is also 32. And we use 64 kernels here. So we also use the same padding, and stride is 1. Can you tell me the output shape of this convolutional layer?
Pardon?
50 by 50, I guess.
The shape, yeah, 50 by 50. The output, the shape of the output is 50 by 50, and how many channels here?
64?
64.
Yes, exactly. So you will know how it works. So after the second pooling layer, it will be 25 by 25, and the channel also 64. Do you agree?
Yes.
Yes.
Okay. And then it uses 3 by 3 kernels, but it uses the same padding, so it will not change the shape of the output. So it will be 25 by 25, and the channel is 128. Yeah, exactly. So you know how to calculate it, right? Okay, so that is the convolutional neural network. And after some convolutional layer and the pooling layer, we will build some fully connected layer, just like here. In this layer, there are 1024 neurons. And in this layer, we have 512 neurons. And in the last layer, because we have 5 different flowers, different kinds of the flowers, so the output layer will be 5. Yeah, we have 5 neurons in the output layer. Okay. And then, yeah, we can train the neural network, convolutional neural network. Here, we will find, yeah, the train laws will go down after 1, 2, 3, 4, 5 epochs. The train loss will go down to 65. We use a cross entropy because that is a classification task, okay? And here, the train accuracy will be 86%, but the test accuracy is only 65%. So what's the problem?
Overfitting?
Yes, exactly. So the convolutional neural network has overfitting.
Pardon? What's the problem again?
Overfitting. So yeah, it means it performs well in training set, but performs not so well in testing set. The overfitting problem. The other fitting means the accuracy of the training set is low. Okay, the performance of the training set is not so good. It called underfitting. Okay. Overfitting means training set good, test set not so good. Okay.
Okay.
So let's take a break for 10 minutes. Okay. Yeah, thank you so much. Hello, you come back?
Yes.
Okay, thank you so much. So do you still remember the answer of the second quiz? So the what's the answer of the second quiz? Oh, sorry. I did not show the... Yeah, can you see that? Okay, so do you still remember the second quiz, the answer of the second quiz? True, exactly true. So sometimes in some tasks, we hope if we input the same data, but the output can be different. So for example here, there's a example here. There's a sentence, I book a book in library. So the first book is a verb and the second book is noun. Do you agree?
Yes.
So if we input these two books into the convolutional neural network or the fully connected neural network, it will have the same output, right?
It should.
Yes. So how to output the verb and the noun? So the answer may different. We need to consider the context of the word. For example, before the book, that is the word I, and maybe the book is just a verb. But before the book, that is a, so the book will be a noun. So how to consider about the context? We need to use a recurrent neural network. Okay, so what is a recurrent neural network? That is here. Just like the fully connect layer, yeah, that is the input. There are lots of time state. For example, that is a time state t-1. That means the word I, and that is a tx, means the book. And that is a t+1, that means and t+2 maybe, yeah, the second book. Okay, so in the recurrent neural network, we have 3 different weights. Yeah, the first one called U, and the parameters were shared in all the states. So this U is equal to this U and equal to this U. And this cycle we call the memory cell, so we can store the informations in the memory cell. And then that is a second parameter called W, and of course they are same. And the third one called V, and of course all the V are same in all the time state. So there, I will give you an example here. The recurrent neural network, sorry. Yeah, here each line means one weight, just like the fully connected layer, except the red line, okay. And the initialized memory cell are 0 to 0 here. And the first word we use the vector 1, 1 to represent. And all the weights are 1, and all the bias are 0, and there's no activation function, or we use the radio activation function. So I will show you how to calculate, how to get the value 2 here. It will use 1 multiply the weight here. So 1 multiply 1, add here. 1 multiply 1. Add here the value in memory cell and multiply the weight here. So 0 multiply 1, all the weights are 1. And use the value in this cell here, multiply this weight. So use 0 multiply 1, and we will get 2, right? So that is how we get the 2 in the memory cell here. And that is same how to get the value 2 in this memory cell. And then we will store the value of this 2 memory cell into here. So we need to update the value in memory cell. from 0 to 2. And then we need to calculate the output of the recurrent neural networks. So we use 2 multiply this weight, so 2 multiply 1, add here 2 multiply 1, and it equal to 4, right? Can you understand?
Yes.
Okay, thank you. So that is same how we get the 4 here. Okay, and then we input the second word, that is 1, 1. So can you tell me how to get the 6 here? Yeah, we can use 1 multiply 1, add 1 multiply 1, add 2
multiplied by 1.
Yes, and 2 multiply 1, right? 2 multiply 1, 2 multiply 1. And then we will get 6 here, right? And then we update the memory cell from 2 to 6. And then calculate the output. It will be 1 multiply 6 plus 1 multiply 6 will be 12, right?
Yes.
So even we input the same value, right? The input are same, but we can get different output, like 4, 4 or 12, 12. Can you understand?
Yes.
So that is how the recurrent neural network deal with the sentence. So the recurrent neural networks is suitable for sentence or voice, just like the sentence has a lot of words. We need to put all the words into the recurrent neural network. Okay, and then if we input 2 here, it will get 32. I will not show you. It's very simple. Okay. And there another kind of recurrent neural network is called LSTM. The full name is long short-term memory. Long short-term memory. So you only need to remember there are 3 gates. There are 3 gates in the LSTM, and that is a input gate. That is the input gate, and it will decide if we need this value, this new value, and this gate called the forget gate. It will decide, should we forget the memory cell in the last time state? And this gate called the output gate, it will decide, should we output the value? Should we output the value? If the output gate is closed, that means it will equal to 0, and 0 multiply anything, it will be 0. So the output gate will decide, should we output gate the value here? Okay. So there are 3 kinds of the gates in LSTM. They are input gate, forget gate, and the output gate. You need to remember these 3 gates. Okay, so why we need the LSTM? Because in recurrent neural network, if the time state is too long, it will cause the vanishing gradient problem. Just like if the neural network is too deep, it will also cause the vanishing gradient problem. So we can use the LSTM to reduce the vanishing gradient problem in RNN. And there's another type of the RNN called GRU. It's quite similar with LSTM, but there's only 2 gates. And it can use less parameters than LSTM, but the performance are similar. So we always use the GRU now and the LSTM now. Okay. These 2 different RNN we always use now. So there's a quiz. The LSTM can reduce the vanishing gradient problem in RNN. You think so? Yeah. Yes, true. Exactly. And there's still another problem called gradient explosion problem in RNN. So we can set a thresholder. Yeah, that means the maximum value of the gradient. So it's a learning rate multiply the gradient. If too big, we can change this value into the thresholder value that called gradient clipping method. And then we can solve the gradient explosion problem. That is true. Okay. The simple method, we just fix the max value of the gradient and we can solve the gradient explosion problem. Okay, and then I will quickly introduce again the generative adversarial net. So there's one guy asks a question in internet. So he don't know the unsupervised learning in recent years. And the young Lacan, he's the father of the CN model. So he asked the question, the adversarial training is a curious thing. So again, proposed in 2014 by Young Fellow. And that is 1, neural networks. And the original GAN, we use all the layers are the fully connected layers. So that is a structure of the GAN. There's 2 parts, the generator and the discriminator. So you only need to remember that we use the GAN to generate the images. And it uses unsupervised learning. Use the unsupervised learning to generate the images or the sentence, for example. Okay, I will show you the result of the experiment. So just open again, file. And I will not tell the details, but just show the performance. In the beginning, it can only generate some noise, but after some epochs, it can generate some images. Of course, we use the data sets are the images. So it can just draw some pictures similar with the images. Just like here, the 8 is beautiful. Do you agree? It generated, yes. It's generated by the neural network. Okay. So you can download the code after the class, but time is limited. We need to, continues. Okay, so the quiz again can use unsupervised learning to generate the images, true or false.
True.
Yeah, exactly. So you need to remember that. Okay. So there are a lot of games. There are more 1,000 different games now. And you can, the name is Cycle Game. If you are interested about it, you can search it. It's very famous. Okay, and next part, I will tell you how to reduce the overfitting problem in deep learning. So there are 3 methods called one or two norms, and we need more data sets. The second method called we need more data sets, and the third one called dropout. So the first one, yeah, the penalties, parameter penalties. It means that is the original loss function, and we can use one penalty item to reduce the overfitting problem. So according to the kinds of the penalty, we can divide into L2 norm. That means add the weight, we use the weight power 2 and add all of the weight to the loss function. And that is a hyperparameter we need to set the alpha. That means how important of the penalty. Okay, that called L2 norm. Okay, and then another one called L1 norm. It will add the sum of all the weights into the loss function. And of course, the alpha is also a hyperparameter. We need to set it according to the test tasks. Okay, and that is the penalties. So do you have questions? Why the penalty can solve the overfitting problem? I will give you an example here. The Y means the loss and the X means the weight. So this line means the training data, and I will use another line. This line means the testing data. And when we train the model use the training data, it will, yeah, go to this point or this point, right? Do you agree? Maybe we will go to this point, maybe we'll go to this point. So if the weight go to this point, and yeah, it will performance well in testing data, just like here, the loss will not be very big. But if we stop at this point, we will get a loss here. Yeah, it's very small distance, but that is a very big distance. That means if the line is smooth, and we can solve the overfitting problem. Yeah, we will not cause the overfitting problem if the line is very smooth. But if the line is sharp, just like this, it's easy to cause the overfitting problem. It called structured risk. Okay, so if we add the penalty here, we can make the line smooth. Okay. Yeah, that is the first measure. And the second measure called we need more data sets. So how can we get more data sets? We can add some noise to the input data, just like the voice, or we can use another words which have a similar meaning and replace the original words, and we can get more data sets. And if the input is the image, we can just rotate this image, rotate it, or just change the shape, or choose part of them. for example, choose the center of this image, and we can get another image. And that is how we can get more data sets. Okay. And the last part, the last method, I will introduce a dropout. So what is a dropout? It's very easy to understand. We can just use part of the neurals when we do the training, but use all the neurals in testing. That is the dropout. It means we reduce the power in training, but enhance the power in testing. And then we can solve the overfitting problem. So do you have any question? We only select part of the neural in training, but we will use all the neurals in testing. It's called the dropout method. It can solve the overfitting problem. Okay?
What does bugging method? What is a bugging method?
Yeah, the bugging method, just like the random forest. So this time we use this two neural, but the next time we'll randomly choose another two neurals. Just like this, it's called the bugging method. Just like the random forest, we will build a lot of decision tree, and we select part of the feature in the data sets and select part of the data in data sets. So there are two random, just the features and the data. So we use different features and data to build different trees.
Okay.
And when we do the testing, we will vote by all the trees. It will vote the final choice. Okay. So that is a random forest, as that is a bugging method. Okay.
Okay.
Yeah. So this paper shows the performance. If we add the dropout here, we can reduce the error rate about 6%. Okay, more than 6% if we use a dropout. So we can reduce the overfitting problem. And there's a quiz. Which of the following method can reduce the overfitting problem in deep learning? That is a multiple choice question. Okay.
All of them.
All of them.
Yeah, exactly. Thank you so much. All of them. Yes, exactly. So the last part, I will introduce two optimizer. So we know we can use gradient descent to train that is a loss. Okay, we can use a gradient descent to train the models from, for example, this point to this point. But we can also use some optimizer to help the gradient descent. There are a lot of optimizer, such as the momentum, I will talk later, and Ada grade, RMS prop, ADEM, and so on. So what is the momentum? Do you know the momentum? Just like we put a ball here, and the ball will fall down from this point. And if we consider the speed in this point, maybe there's no gradient here. There's no gradient here. But the ball has the speed, so it will go up. Even the gradient is this direction. So that's called the momentum. So we can use the momentum to drop from the local minima, for example, here, and yeah, it can train the model quickly. Do you agree? Okay, that is a momentum. And another one called the ADEM. So what is the ADEM? It can change the learning rate during the training. So such as, do you know the golf ball?
Yes.
Yes.
So in the beginning, I'm here and the ball is here. And that is the target. We are far from the target, so we need to use a bigger learning rate. For example, we hope click the ball and to this position. We can use the big learning rate. Do you like my drawing? Can you understand?
Yes, yes.
This position, we are here, far from the target. So if we hope we can train the model quickly, we need to use a big learning rate at the beginning. But after some epochs, yeah, it's close to the target, just like this situation. We are close to the target. We need to use the small learning rate to get the target. Okay, can you understand?
Yes.
So the ADAM just hope we can change the learning rate from the big value to the small value and during training, and it will consider the momentum together. And so it will add the momentum and the adaptive learning rate. Okay, that is the ADAM. So we always use the ADAM now. Okay, can you understand?
Yes.
Okay, thank you. So let's compare the momentum and the ADAM. The ADAM is the orange line, so it performs very well in testing set, training set, sorry, in training set. And this line is the momentum. Yeah, the brown one here. So the training accuracy is not so high, but the testing accuracy here. The ADAM is the original line, just like this line, and the momentum is the brown line. So the testing accuracy of the momentum is higher. So maybe the ADAM is easy to overfit, but the momentum can solve the overfitting problem. Okay. So the ADAM we will use in the BERT proposed by Google. That is a model, very famous model. We can use it to extract the features of the words, and it use transformer. That's a very new type of the neural network. So that is a BERT. The BERT use the ADAM, and the ResNet. Do you know the ResNet? The very famous convolutional neural networks in image classification task. It's very deep. It has 152 layers, very, very deep. So the ResNet use the momentum, and the Euro use the momentum also. Okay. So the momentum can maybe reduce the overfitting problem, but the ADAM is more quickly. Okay. So that's a short summary. The momentum updates slowly but stable, can reduce the overfitting problem, but the ADAM is updated quickly but easy to cause overfitting. Can you understand?
Yes.
Okay. So the quiz. Which of the following optimizer can be used in deep learning? Actually, all of them, I will tell you, that is a gradient descent, normal gradient descent. And it is a momentum I talked before, and that is RM's prop. It only care about the adaptive learning rate. Adaptive learning rate. Only care about the adaptive learning rate, but the ADAM care about the momentum plus the adaptive learning rate. Okay. So all of them. And finally, I will briefly introduce the application. Actually, I have introduced it in the first day. We can use the deep learning in game, such as the AlphaGo, and we can use into computer vision. We can use a convolutional neural network in computer vision, such as face recognition problem, and the NLP, and we can use RNN or transformer in NLP tasks, and we can also use RNN in speech recognition problem. The RNN performs very well in speech recognition task. There's a model called RNN transducer or RMT. It performs very well in speech recognition task. Okay, and that is all for this class. And there's 2 quiz. Yeah, there's 2 quiz. Do you know that? The framework, not deep learning framework, not.
Is it buffer?
Yeah, buffer. Buffer is not the deep learning framework, exactly. So it proposed by Microsoft and the Keras we used. And okay, that is also one of the framework. And again, it's a deep learning method. Of course, it's yes. Use unsupervised learning to generate some images and sentence. Okay.